So, welcome to a new edition of the Heat Treat Podcast. My name is Carlos Torres, your host, and today we have a super guest, one of the greatest scientists and metallurgical engineers on heat treating, John Chip Keough. How's it going, Chip?
Good. How are you today?
I'm doing fantastic. First of all, I find it strange to call you John because all my life I had called you Chip. I would like to begin asking you how you became Chip.
I been Chip since I was a little baby boy. Somebody told me there's a saying that when somebody is very energetic, they're very chipper.
Okay.
And somebody told me I was too chipper to be a John.
Which you are. You know, since I know you, you've been right on the stage, you know, promoting the technology, promoting the industry. You've been a great marketer and advertiser of the heat treat industry. Let's start with that. And today we're going to focus on the Austempering process. And I believe we got the best guy to talk about this. And I would like to restate our mission of the podcast is to deliver information about the heat treat industry by power players using social media and technology. So I will call you Chip for this interview. I don't want to go that formal because I had called you Chip all the time. I hope that's fine with you, Chip. So you were born and raised on heat treat.
I was.
So can you tell us a little bit about what was your first job? I know your father was one of the founding fathers of heat treat in the United States. So can you tell us a little bit of that family history?
You know, my father worked at surface combustion in his early career, and left there. And after some time, he invented the first continuous atmosphere to salt furnace. Up until that time, Austempering process was very expensive because it was done in baskets, salt to salt, and 1,000 pound an hour atmosphere to salt furnace that made clean, beautiful gunmetal blue parts was a big deal. And my first, you know, I used to, when my dad was starting his business in 1962, I'd follow him around, and on the weekends, you know, I would be in there. And my first job I remember doing is sweeping small clips and clamps onto a charging conveyor for a continuous furnace.
And how old were you at that time?
You know, I want to say I was 7 or 8 years old.
Okay. And when did you decide to become an engineer and devote yourself to this industry?
Well, this industry was a secondary thought, but I knew I wanted to be an engineer from the time I was a little boy. I was always taking stuff apart and putting it back together, and so it was just a natural for me to go into engine school at the University of Michigan. And I went in as a mechanical engineer.
Oh, I didn't know that.
But there's a long story about how I needed more work. We can't get into that in here, but I needed more money. I was married with a baby, and I knocked on a door to a professor who was the metal casting professor at the University of Michigan. And he, the first time I saw molten metal poured, I was hooked. So I went for a dual degree in mechanical and materials and metallurgical engineering is what they called it at the time.
So that was your first approach to castings when back in university, and
Right.
and after that you graduated, and reading your CV, you went and worked for a bunch of companies. Well, not a bunch, but you know, very big companies, and specialized on the casting process. Will that be accurate?
Correct. I made gray iron blocks and heads for General Motors, and then I made super alloy turbine blades for TRW Turbine Components Division as a process engineer, working as a process engineer.
And while you were there, did you have any heat treat responsibilities, or just castings?
Just castings, but in the small world category, one of the first big applications of Austempering ductile iron were ring and pinion gears for General Motors rear wheel drives.
Mm-hmm.
And they heat treated those in the building next door to where I worked at Pontiac. And so I knew a lot about that process going in.
And during that time, your father was already working. Well, he had started his own company, I assume, AFC at that time, right?
Yes, and plus a commercial heat treat in Detroit, controlled atmosphere processing, Capco. And my brother had joined the business right out of college. And so I was off on the fast track in the casting world. And they called me and said, hey, we've got this Austempering specialty. And there's this thing called Austempered ductile iron that's just now appearing on the horizon. We don't know anything about castings. Are you interested?
And you do, and you did know a lot about casting by that time. Well, I don't know if a lot, but well, you were in that industry.
I knew enough, and the prospect of doing that was pretty good. The first couple times they asked me, I said no because I was doing quite well.
You were happy where you were.
I was happy and fast tracking and everything else. I mean, I was a young process engineer working in a factory with robots and air conditioned rooms and
the American dream.
But I really did want to work with my dad at some time, and I thought this would be the time. So in '84, I joined the business, and my brother and I immediately incorporated applied process around the UBQA technology that had just been developed.
And applied process was like the branch for Austempering from your group. So there was at Monster Furnace Company, AFC, which was the company that actually designed and built furnaces.
Yes.
Correct me if I'm wrong. And then applied process was the specialized branch for commercial Austempering work. Will that be accurate to say?
That was all batch. Applied process is all batch heat treatment. We had a continuous Austemper shop in Detroit and one in suburban Detroit. So there were two continuous Austemper shops in the Detroit area in that group.
So like the big change was there were the two companies incorporated there, but when you came and work on the family company, you co-founded Applied Process.
Correct.
And the mission was to heat treat on the Austempering process on a batch IQ furnace devoted for Austempering.
Right, the kind of parts, larger and thicker parts that would not be appropriate for a belt furnace, and
bigger parts, casted parts. So we had dinner many some years ago, and I recall you told me that one day you were working on the shop with a mutual friend of ours, Gordy Cargill, and Gordy told me this story that you actually went and took a plane to do some skydiving, and you broke a leg. And you got in trouble with your father because of doing that. Do you mind sharing that story with us? I mean, it's just an advice for the kids that work with their fathers as presidents, and they want to get into trouble. But I don't know. You wanna, if you're comfortable sharing that with the audience.
As you know, running a family business is about 50% business and 50% running.
You can. I know what's it like. Trust me.
And well, at that time, I was in college. I was working nights, and AFC had just built the building that they continued to be in. We were welding some huge furnaces that we were welding these panels and bricking panels for a huge furnace that was going to General Motors. I was doing some drafting work and welding and some other things, you know. And I jumped out of an airplane on the advice of a friend, and I broke my leg on my very first jump. And it was a holiday weekend, and I came in on the Tuesday on crutches. And my father said to me, what the hell happened to you? And I said, well, I broke my leg. And he said, well, I can see that. You know, how did you break your leg? And I said, well, I went skydiving. And he said something to the effect of, you are married with a small baby, going to school and working full time, and you jumped out of an airplane. That was a pretty damn fool thing to do. You are fired. And he fired me, and it was not a joke.
And then you went to the casting industry, I will assume, right?
That's exactly what happened.
So,
I lost my job at AFC, and I went, knocked on doors, and got a job working for a metal casting professor.
So if you hadn't jumped out of an airplane, you wouldn't have the ability to help build Applied Process. Will that be a fair statement?
It is most likely that I probably would have never joined the family business.
Well, I'm happy that everything turned out well.
It did, by the way, and
it did.
You know, working with my dad and my brother was a great experience, and I think we did it right.
I had the pleasure to work with your brother, Bill Keough, as I called it, Mr. Keough. That's what I find it very funny to call you Chip and your brother, Mr. Keough. And I must say, he's a great businessman, a great leader, and a very dear friend, personal friend. So all the best to Bill. But you know, today you're the guest. So building Applied Process, metallurgy, castings, and your passion to innovate, study things, right? Can you tell us about when you decided to design IQ furnaces, which is called the UBQA, furnaces specialized to heat treat much bigger parts than just in regular belt, and the Austempering process? Can we go a little deeper on, well, let's start with the basic. What's the Austempering process? What are the goals? How is it done? So if you were to explain to the Austempering process, how will you explain it to a class? Because I believe you teach also in the Michigan University, right?
I'm an adjunct professor with material science and engineering at Michigan.
Okay. So when you have to give the class about the Austempering process, how do you start?
Well, the Austempering process is, let's first talk about the quench and temper process so that I can compare.
Totally.
In a quenching and tempering process, a martensite process, we heat the steel or iron to a temperature that's fully austenitic. Okay, so the whole structure is austenite. Then we quench it down, cool it down fast enough to avoid the formation. And in a martensite quench, we quench to below the martensite start line. And at that point, as each part of the casting gets below the martensite start temperature, martensite forms basically at the speed of sound. And then you have a hard part that is subsequently tempered to give it the toughness or the hardness that you want. The problem with that is that parts have different thicknesses on them, and so they transform at different times. And so if you have a part that comes down and the thin section transforms to martensite, it's already grown and hard. You have this austenite next door, and now the austenite next door goes to change to martensite. And that's when you get the distortion or cracking that we fight in quenching and tempering. It's a non-uniform transformation that does that. Austempering, the beginning of the process is identical. We heat it up,
Austenize.
get the part fully austenitic. We quench it down fast enough to avoid the formation of perlite, but we stop it at a temperature above the martensite start temperature. And we hold it there. And over many minutes or hours, the entire structure transforms uniformly to a bainitic structure. Okay? In steel, that structure is asecular ferrite and carbide. In cast iron, because of the high silicon, the structure that we get when we austemper is asecular ferrite and carbon stabilized austenite. And that's called auspherite.
Auspherite. That's a new skill for me today. Auspherite.
Auspherite. And the other one, of course, is bainite, named after Edgar Bain. That was back in the 30s that was developed. So, you know, there's, to do this in the furnace, right? You have a large salt bath. In the old days, some lead bath was used, but we don't do that anymore. In the old days, we used cyanide salts and other things, but nowadays we don't do that. You have to have some way to austenitize the part where you don't decarburize the part.
That's on a furnace under atmosphere, right?
Yes.
So and let me just get into that just a little more detail. So basically, on the austempering process, what we're doing is that we're heating the part above austenizing level, and what really changes from the other processes is the quenching media. Will that be accurate to say? So the key, or like the magic really, where you have to focus on this process, it's on the quenching media and control the process variable through that quenching stage. Would that be accurate to say?
Correct.
Could we go a little deeper, because you just stated that it can depend if the part is on the quenching media, but at temperature, but it can be just, I believe you say, from minutes to hours. What's like what's like the driver there? Because when we go on oil, we just want to quench and we go at the very low temperature, or water, right? But we do not try to stabilize the load for long times for long periods of time. Why do we have to do that on this process to get the microstructure uniform?
Yes, and it would be a corollary to tempering. You know, different furnaces, different materials take a longer time or a different temperature to temper them. Okay, there is a bainite start and a bainite finish on parts, just like there's a martensite start and a martensite finish. And so, for instance, in something like a 1050 steel, austempering at 350 C, you know, in 5 minutes, bainite.
Bainite.
Okay?
Mm-hmm.
But something like a 52-100 steel, austempering at 260 C might be many hours. So each alloy has its own time for a bainite finish. And in cast iron, because cast iron has 3% carbon in it, you know, over 3% carbon, you know, the time to complete the auspherite reaction is longer than steel, because the silicon changes when the finish line is. So that's the difference.
And let's talk about one rule of thumb that might not be accurate when we talk about Austempering, because some teachers, some metallurgists always claim like after every quench there is a need for tempering process, which don't seems to be the case in this process. So when you quench on salts and you maintain, are you stress relieving as well? Would that be fair to say?
What you're, if you're neutral hardening and you're
Mm-hmm.
not applying a case, okay, when you are transforming in the Austemper bath, it's a very low stress process. It's not like martensite quenching. In martensite quenching, you get very high stresses and they're not very uniform.
Because of the thermal shock.
Because of the non-uniform transformation, not the thermal shock.
Got it.
It's because different places in the part transform at a different time. With Austempering, the whole part transforms slowly at the same time.
So there's the stress is much smaller than going all the way.
It's why you don't get hardly any distortion. You get very uniform, small uniform growth, but very little distortion.
We talked about one of the some of the misconceptions of the Austempering process, and one of them, maybe you just stated, but we can go deeper into it, is like you don't get distortion because of the thermal shock. That is not correct. It's because of the transformation is more how do you call it? More structurized, more uniform.
More uniform, and it happens over time.
Over time, not on a peak.
Reaction happens when you're 1 degree above the martensite start line. It's austenite. When you're 1 degree below the martensite start temperature, it's martensite. Mm-hmm. And that transformation from just above martensite start to just below martensite start happens at different times on the part. If you could magically wave a wand and get the whole part to convert to martensite instantaneously at the same time, it would just grow and there would be no distortion. There would just be uniform growth.
So the quenching media, as we talked, is really the key in here. What are like the common practices that you need to do in order to maintain a good quenching media? Because I know that you have to be maintaining the salts, measuring the pH of the salts in order for them to work properly and have a right transformation. What will be a common a best practice in order to maintain a quenching media as a salt?
Okay, we use atmosphere to salt only. We don't use salt to salt. The salt to salt people have to deal with the drag out of the high temperature salt into the low temperature salt. And they have to do a lot of measuring. They have to desludge. They have to do other things to control it. We using the salts that we use, sodium nitrite, sodium nitrate, and potassium nitrate. You blend those to get a certain melting temperature, and you just control that. You control the chemistry of the bath. pH of the bath itself is not an issue. When you reclaim salt from wash water, pH becomes an issue. But it's very, sodium nitrite is a food preservative. Sodium nitrate and potassium nitrate are fertilizer. And what you do have to control is that you don't get carbon sources in contact with the nitrate salts, because that's an infobomb. That's why it was so important to develop a separation. If you wanted to keep parts under atmosphere, you had to come up with a separation between the high temperature furnace, which is a controlled carbon atmosphere, and the salt. Because if you snow carbon in there, you can have a fire or something like that. So there's a safety issue. But those salts are fully recoverable from the wash water, and you can use them over and over again. The one thing that I would caution you is some people in the past have chosen. So
Chip, I lost you for a second. Could you repeat that? Could you repeat that, please? You know, I believe that's very very valuable. Could you repeat the last advice about the percentage?
Yeah. If you mix, let's say 1/3 sodium nitrite, 1/3 sodium nitrate, and 1/3 potassium nitrate, okay, you'll get a salt that has a melting temperature of, I don't know, 350 F, you know, maybe 200 C. If you use sodium nitrite, that has a melting temperature of like 300 F. If you use the nitrates, you can get a salt that has a melting temperature of 550 F, okay? But a salt with a higher temperature, although it's cheaper, you'll drag more out. It'll come out on the baskets and on the parts. You'll drag more salt out of the quench. Salt with a lower melting temperature runs off the parts very well, and you don't drag it out. But if somebody tries to buy the 2 cheaper salts, they're fine as long as you just agitate them and never decide to add any water. Because if you try to add water to increase the quench severity, which is a trick that we use to make the quench faster, you create nitric acid, HNO3, and it destroys the tank and any kind of elevators or anything you have in the tank.
Because of corrosion?
No, it makes acid.
Oh, well, yeah. So that's another conception about whenever we use salts, that the trace because of the acids or the, you know, they distort a lot, and they don't last as much as oil, and maybe some of the tanks we get a bunch of leaks because of maintaining the salt. So the better you maintain your salts, the less you get these impacts on the equipment or elevators or trays. So the chemistry of the salts, if they're maintained correctly, will they give you a longer life on those devices?
I think that's a minor effect.
That's a minor effect.
The major effect is the thermal expand. I mean, if you're running a tank at 700 degrees F, there's a lot of growth and movement there. And so the defects that you would experience, aside from the case that I just described, okay, the defects that you would be fatigue, would be thermal fatigue, not due to any kind of acid reaction or anything like that. So the one case I spoke of, that if you mix the 2 nitrate salts together and add water, you've got trouble. And it's immediate and it's catastrophic. The other one, using these high temperature quenches, and lots of it, you know, it has you moving the tank a lot, and you have these thermal fatigue.
And the salts have to be at after you melt the salts, right? They have to be kept at a certain temperature forever, right? You cannot have the salts without heat on them, otherwise they're gonna
Solidify.
They're solidified, and you're gonna waste a quench tank. Am I right?
Yeah, but you would, before anything would solidify, you would pump it out.
That's where I was going. So typically these systems, they have a salt holding tank. So in the event that you want to maintain the tank, or you want to work on the tank, I don't know, take an agitator out or work on some steel, you will have to pump all the salt to another salt container, which is like a standby salt container, at a certain temperature with a certain agitation in order to be able to work on the tank. So that's like another need for this process, because once the quenching medium is melted, the salt, and you always have to have some agitation on it on certain heat.
Right, unless you choose to solidify it in some smaller containers.
How do you solidify it in smaller? I never heard of that.
Well, just you can put salt in a big ice cube tray, if you will.
And they'll melt till again?
Yeah, you can take them out and then put them in a bath.
I didn't know that.
Yeah.
And also, I believe salt quenching right now has like it's becoming like the fashion process right now. Too bad. Right now you're in Joyworks, but right now I believe everybody's talking about the beauty soul, or everything that you have talked about for the last 20 years. Like the world right now is like switching and changing. One of the claims is that salt is green, that we can actually recycle it, and that's not the case with oil. So, how much percentage of the salt can be recycled back?
100%.
100%.
Now, that being said, sometimes you get, you get some things in there. You can get carbonates. You can get, so there's certain techniques that I won't go into detail with.
Right. That's the secret. That's the secret sauce.
There's some secret sauce there, but they can be reclaimed 100%. But I will add that if you have to run these salts down the drain, they are not harmful.
They're not.
They are not. They're regulated and everything else, but they aren't harmful. They aren't poisonous. This is not cyanide salts. This is nothing like that. And like I said, sodium nitrate is food preservative.
Mm-hmm.
And potassium nitrate is fertilizer. So it's they're not a problem, and you can use waste heat. You can do a lot of things, but you can recycle salt. But I am certain at the AP shops, we have some salt that's still been going around the loop since 1984.
And I believe that's one of the pros of this process, because one of the big cons with oil is that you cannot drain it down you cannot drain it, right? Because that's poisonous. You can actually contaminate water. So salt is green, is recyclable, right? So
it doesn't smoke. We don't get smoke. The shop is now. You don't want to mix oil quenches with salt quenches.
Great topic. I mean, and you and I have had the discussion many times. But let's explain why. Because either you believe it or not, I have some customers that I go, and these are big companies, like big transnational companies, and I go there, and just on a regular sales call, and there's oil quench line, a mesh belt, a continuous furnace, and next to it there's a salt furnace line. And I always think about yourself and say, this is a bomb, right? Can you explain the chemistry and why it's not convenient to have salt and oil together? And I'll tell you why. Every time I tell these customers that this isn't supposed to do, he states, well, on an oil quench furnace, you have a washer next to it, right? That's the answer I get. And it's kind of fair, But what's your opinion on that, Chip?
Well, the last time the Keoughs had oil and salt in the same building was 1967, and we burned a factory to the ground. And I can tell you that salt and oil will create a fire that cannot be put out. If it's only a fire, it can create a huge explosion. Again, a fertilizer bomb is potassium nitrate with diesel fuel, right? A fertilizer bomb that's very destructive is potassium nitrate with diesel fuel. If you take Quench oil and put it on potassium nitrate, same thing. You light it off, it's a bomb. Those people who have those furnaces right next to one another are just gambling. And one time when some oil runs here into there or some salt gets there, they'll have a fire.
Which eventually it will, right?
Yes, they will have a fire they can't put out. So I would never, ever, ever recommend that anybody, without taking issues on both ventilation and isolation, I would never put them in the same building. You know, if you put a salt furnace over behind a block wall and it has separate ventilation from the other one, everything else, you may be fine.
So on a more modern expression, salt and oil should have social distancing.
Yes, yes.
Right. Okay.
Masking and
masking, right? So that's a fun way to teach at university to the new guys.
Yeah.
Because now the third social distancing is super fashionable. So salt and oil, social distance, right? So and just a mask.
Please.
So let's talk a little bit. Let's compare the quenching media. So we got oil. We talked a little about that. We got water, and then we got polymer and salts. What are the costs of the process compared to conventional oil and water? Because we in this particular quenching media, you need to have heat on it. Also, I believe also recirculation, I will assume, right? Of course, what you want to obtain are different microstructures, whether you quench with oil, water, polymer, or salt, right? But there's the constant battle that some of the oil quenching it cannot be converted to salt, and salt cannot be converted to oil in particular process. But you and I, speaking before the interview, there's a place where both processes are effective to get the hardness of the steel. When are parts compatible with both process, with oil quench and salt quenching?
Oh, well.
And sorry to put you on the spot, but I believe this.
In salt quenching, I can quench to martensite, or I can Austemper.
Mm-hmm.
I can't Austemper in oil.
You can't.
In hot oil, there's some hot oils that can get up to 450 F, but that's the very low end of the Austempering range. Salt is much more flexible, and quite frankly, with the way that the UBQA equipment operates, we get a quench severity that's better than fast oil. And so we can actually through harden thicker parts when mark quenching than with oil. And I would also bring up the point, so it has greater flexibility. And you mentioned that we need to spend money to heat the salt, and we don't have to do that with the oil. What are you doing with an oil quench that's running in continuous production? You're cooling it, right?
Mm-hmm.
Why is that? because you're taking all those BTUs out of those parts and putting them into that bath. Guess what you spend most of your time doing with a salt bath? Cooling it, because it gains temperature when you quench a hot load. So once you get it hot, and then you start running continuous production in it, you spend much more time cooling it than you do heating it.
Oh, okay. Makes sense.
And it's 100% reclaimable. So there's no advantage to oil.
Great, great. Great, great answer. I never thought of that way. So let's introduce to the show the concept of ADI, right? You've been talking about ADI. There's videos of ADI, but it's Austempering ductile iron, right? How can you explain this concept to? We talked about Austempering. We can also talk about mark tempering, which is other process, right? But when it comes to the concept ADI, that's the iron itself. How was it created? The applications of it. What do we need to watch it for? How different is from other irons or steels? Can we go into that?
Certainly. The basis for ductile iron, the basis for Austempering ductile iron is a material called ductile iron or spheroidal graphite iron. And in SG iron or ductile iron, we do some magic with, say, magnesium or rare molten metal bath to might form as round spheres. And if you just cast regular gray iron, the graphite forms like cornflakes, little cornflakes all throughout the metal that are like a crack, right? But now imagine we can make the graphite into little spheres with a metal matrix all around them. Now we can exploit the properties because we don't have these connected graphite notches. There has changes the behavior for heat treatment. But when we austemper ductile iron, we get a material that is 2 times stronger than as-cast ductility. It's the lowest strength grade of ADI is 3 times stronger than the highest strength grade of cast aluminum. And it only weighs 2.5 times as much. It's only 2.5 times more dense. So it has a very high strength to weight ratio. And it's low cost. The base metal is iron. And aluminum is 3 times as much per kilo as iron. And so it's a low cost, high performance material. And that's why it's caught on. Ductile iron was invented in the 40s, and now worldwide there's 27 million tons of it produced every year. And Austempering ductile iron continues to climb up and the process to understand it.
So now that you stated like that, so it's a low cost iron that it's very strong, stronger than some other steels or irons. So the applications of this Austempering ductile iron are meant for very tough performance, right? So we got the constructions, we got the mining, we got agricultural. So the main application for this is for applications that required, let's say, hardness and wear resistance. Not wear resistance. How would you call it?
A combination of. It depends on the application, right? Just like steel,
right?
It depends on the application. It's in applications where you need a high bending strength.
Okay.
You can have high bending strength. There are grades that are high wear ground engaging parts. There are parts that have to take ground engaging and impact, and
Impact. I was looking for impact. So my conception is that some of the parts are going to have a great impact, and since this and they're gonna break eventually, right? But because like a drill or something, right? A constant impact. But the ADI gives you that low cost, super strong iron that will be able to last much more time than regular steel or other type of iron. That would be like the main application.
right. And like any other material, there are certain applications that's perfect in, and there's certain applications you say, no, ADI wouldn't be the best solution for that one. Something else would be a better solution. But you can't drive by a semi truck on the highway without seeing ductile iron and ADI parts hanging down on that truck.
And I recall that when you were president and CEO of Applied Process, you used to work a lot shoulder with shoulder with the foundries. Can you share with us like a success story when you told the guys, I know what you're doing, you're using this type of iron, but I got the solution for you, which called ADI, and this is how we're going to improve your cost, and we're going to improve the strength of the material for the application. I believe you have a ton of that, I will assume.
Yeah, I may not give you a specific example for market reasons, but if you say to the ductile iron industry, okay, here's an option to make your material twice as strong for a given, and when you add you're still 15 or 20% cheaper than the competitive material process. What happens is the ductile iron foundries say, well, I've got a customer that has 3 applications right now that are welded steel or that are aluminum or that are steel forgings, that they could really take some money out of these by doing this. And so the ductile iron foundries go in. We're just the heat treater, right? We're just heat treating. The ductile iron foundries customer is buying the part, right? And they're applying the part on their agricultural equipment or on their earth moving equipment or on their truck or on their car. So the ductile iron foundry becomes engaged in the selling process. Okay, you won't ever see your mill steel place getting involved in your sale process on shafts, let's say, or something. You won't see them doing that, but it's in the ductile iron foundry's interest to promote Austempering ductile iron.
So I believe you love to work on designing the whole process, switching from one iron, from one steel to Austempering ductile iron, because you knew actually the science, the material science behind it, and you knew that this iron was it was more cost effective, and it would outperform the other steels or irons in the market. And that's like everybody wants to have that. Like, hey, customer, I have a solution that I can help you, get better profit, have a happier customer, and we know how to do it. I mean, that's like the sweet spot of every business, to be able to approach your customer and say, I can make you save some money.
Well, and before ADI, you have all the ductile iron foundries competing against one another there, yes? And they're competing against one. Now comes Austempering ductile iron. They can pay for that service, add margin on top of it, and still come in lower cost than a steel or aluminum forging, casting, or weldment. And so immediately their margins go up, and instead of competing against the other foundry, they're competing against these other material process combinations.
So we can say, and we don't hear this much in our industry, but let's say the discovery of ADI was a disruption to the industry.
That would be true. That would be true. And
Yeah.
I am really happy to have been a part of commercializing Austempering ductile iron.
Now, so we talk about ductile iron foundries. Also, we talked about the applications, but now that well, you had a you still have a great career, right? Speaking in many seminars, I believe I saw you one time in Germany, many times in the United States, talking about the stemper ductile iron. Uh, but now you're devoted yourself to a new project of yours that it's called Joyworks Studio, right? Can you share a little bit about that? What Joyworks is and what you're doing over there?
Yes. I built the Joyworks Studio across the driveway from 2005. And I have melting capabilities there. And it's really my place. And I can pour 200-pound heats of iron. I can run experiments right now. I'm doing some subcontract work for a tech startup. My product there really is I always have some college engineering interns working there. And so my product is those young people. But I try to bring in just enough money to pay for that. It's not a profit center, it's to R&D. And I collaborate on certain projects, university projects, private company research. We do some artwork. We teach classes there. We bring in the Boy Scouts, and so it's just fun, and I like doing it. I don't make any money doing it, but I have a great time.
Well, I believe you have well earned that you're actually right now doing that because that's your passion. You can tell just speaking to you and that you really love what you're doing. But years ago, you were all over the world traveling. Talking about Austempering, the technology. You had some investments in China. I believe you had a lot of licensing of technology in Europe. Of course, the great success of your heat treat shops on the United States. From becoming like the main guy on Austempering and a super successful businessman, right? Now that you can share that experience and you can teach young kids, young engineers, and say, I have a hell of a ride on the last 30 years, and this is the knowledge. I believe that's really valuable, and I think that's your way of making this world a better place. And if there were more people like you, which was not, which was as comfortable as you teaching kids what you have learned through your entire career, this industry will actually grow exponentially, and we will have more disruptive technologies or new irons discovered or new applications because if we compare our industry with other industries, there's been very little on disruption. And as you and I just stated, maybe ADI was one of the latest. Of course, there's controllers and innovation stuff, but we're still hitting stuff and cooling it down. But designing an iron that can go to an application, not many people do that. So I believe that is what's very unique at yourself. You're a heat treater, but as well, you are a material engineer, and you actually design an iron.
Well, early on, I'm really a process engineer that has spent a long career learning how to be a CEO and those kinds of things. I'm a process engineer. I love it. I love everything about process engineering. Early on, I did something that was unique to the industry, I think, was put in a full-time R&D, a fully staffed R&D effort at Applied Process.
You had you had PhD guys there, right?
Yeah, and it continues today. And these applications and everything else, we could put people full-time researching these, helping the customer, holding their hand, and develop new products. There are companies whose products who came into existence to design a certain ADI or carbo austempered steel, which is another thing that we developed. And so we chose to specialize in austempering. We chose to have a fully good R&D effort. And by doing that, we've been able to come up with these new and sometimes disruptive, excuse me.
Not a problem. Not a problem. So I believe the company you co-founded, it's one of the examples that you can tell that R&D does pays off, because it is unusual for a heat treat shop to have an R&D department, because that adds a lot of overhead. But in your case, you're a true believer of R&D on material science, on process, on trying to innovate. And I believe that's what is unique about yourself, especially because there are many guys that run heat treat shops, but they just call themselves, I'm a heat treater. And you just define yourself as a process engineer, which I found it really amazing, because you were named many years one of the most influential, and you're truly an engineer for what we called heat treat applications and castings. And which brings me to the other part of the podcast, which is called heat treat hack or heat treat gadget. Do you use a heat treat hack or on your daily routine when you walk your heat treat shops, or do you have a heat treat hack that you can actually share with the newbies? All years of experience, you must have learned something, a trick or two. Would you be comfortable sharing one with the audience? Maybe I can learn a hack today and apply it to my heat treat shop today.
Yeah, when I'm traveling down the road, there's a certain time of year when the trees give off the small floating fuzz in the air. Immediately that reminds me to call the plant services guy and tell him to change the filters on the endothermic generator, because they will plug up until the generator is not operating properly. And that's just an old thing that I developed over the years, and I'm just reminded.
How many years did it take you to learn that?
It must have been about 25 years ago that it happened to me the first time, and ever since then I've always remembered to do that.
So do you still call the guy at this time, or do you have a guy that actually is watching for that every time?
I still do. Well, actually, now I text them. I text them and tell them, hey, it might be time that the fuzz is flying. It's time to change the filters.
That is fantastic. That's actually a great hack. I mean, this is the section when you learn all kinds of stuff, and you get very surprised about what you hear. Right? Everybody has their own hacks that they have learned through their entire career, and I mean, this is a great hack. Let's talk about a little more. Like a trending topic nowadays, energy, right? Global warming, right? Energy utilization. We talked a little about how we actually used to heat up salts or cool down the oil quench or vice versa, right? But heat treat, it's said that, or maybe the urban legend is that heat treat does contribute something on global warming, right? And I know that you have a great policy on energy utilization and how you can actually improve the efficiency of energetics used in our processes. So can you tell us a little bit, or what do you do, or what do you believe is the way to go greener? We talked a little bit about how salts are super green and they're fully recyclable, but the nature of the process ask for a lot of energy to hit parts, very big casted parts. The nature of the process sometimes requires oils and remains of salts. What's your approach on energy savings?
It's between CO2 and climate change. And we could argue about that for a long time. The point is, again, as a process engineer, all I can do, I can't handle the global politics of environmental anything. But what I can do is constantly look to use fewer BTUs, joules, kilowatt hours. It's based on using less of the. I'll be doing the right thing. Stop worrying about which type of energy you're using, that one is better or worse than the other. What you have to worry about doing is using less of it. And all these techniques that we use now, recuperative burners, using waste heat in gas, using heat exchangers to get all of these things, the lights, using LED lights, every one of those things matters. So my big advice to people on the whole issue of climate is, don't get into that rabbit hole. Just focus on constantly using less energy. And if you do that, you'll be making the right decisions.
Yeah, make your energy efficient. Don't have big wastes, or you can actually upgrade your system and use more efficient burners.
Increase
recuperate hot air. So I believe
maybe
that's what you're
track,
referring, right?
Maybe track, for instance, kilowatt hours per dollar of sale, where you capture
all KPI.
All the gas, all the electricity, you capture all of that and put it in, not in dollars or kilowatt hours, per dollar of sale, per unit of sale. And if that number is constantly going down, you're moving in the right direction. You're doing the right thing.
That's a great way to look at it. I mean, we have to have or little effort, and if we actually get all of us moving in that direction, we can make a difference saving energy.
That you can focus on. You as an individual, you can't focus on climate change, BTUs per unit of sale. And then you're doing the right thing for your business.
Also, you're making profit if you're using energy more efficient.
Absolutely.
So, just to conclude the show, Chip, we've been talking about Austempering, we've been talking about quenching media, ADI. It's great to have these inputs from yourself, a process engineer, which became a CEO of many companies worldwide. China, shops in the United States, now has their own R&D center in the backyard. Professor of the university, right? I always like to close the show with what would be a personal advice. It can be an experience you had or something that you learned through your entire career that you would like to share with a young material science engineer that is looking for a job, or maybe he wants to specialize on heat treat, maybe it can be on castings. What would you share with him? Imagine if you were to give an advice to yourself, you could travel in time and you can tell something to John Chip Keough, right? Back when he broke his leg and he was about to enter the casting industry.
There is a common thing that I say to students when they're getting out of school, because generally they don't know what they want to specialize in when they're leaving college. Say yes. when they go to their employer and the employer says out loud, there's this problem that we've got. I say to that person just to raise their hand at problem. They can't do themselves any harm because nobody else has solved the problem to date. Odds are they'll find a way to solve the problem, and then they'll know how that's done. And their boss will look at them and say, wow, that's amazing that they volunteered to do that. And then along the way, if you say yes enough times, you can become the king of that. And it's nice to know a little bit about everything, but it's great to be the king of something. And you will find that out along the way. But to get there, you have to say yes to problems that going in, you don't even have any idea how to solve them, but you will solve them. So that's
so basically
my piece of advice.
Is not to be afraid to raise your hand and say, I'll figure it out.
If they're to date, then you have no risk at trying to solve it. Even if you can't solve it, you come back and say, I tried this, this, and this, and it didn't solve it. Your boss is in no worse position than he was when he started because nobody else had solved it either. So just say yes and go in and solve the problem and learn that skill and move on. And that's where experience comes from.
Yeah, sure. Say yes, check out what the problem is, do some research, talk to people, analyze it, use that critical thinking, that engineering skills that you acquire in college, and try to bring a solution. Maybe it works, maybe it doesn't, and try the next time until you figure it out. And
you'll immediately earn chops.
Totally. I believe that's a great advice, and that is an advice for the young audience. I don't know where you are. Maybe you can be in Latin America, in Europe. This guy really knows what he's talking about. He's one of the most influential CEOs in the heat treat industry. So follow that advice. I'm following it, right? So Chip, it's been great having you here. I hope this is not the last time that we speak, because I know that you have much more knowledge on some very detailed topics that we would like to talk to you about. I would like to say thank you. It's great talking to the legends of the heat treat industry. We're working very hard to get there, and this podcast helps me a lot. To share information, but for me, it's also a great learning experience. Thank you very much, John Chip Keough, one of the greatest CEOs and process engineers in the motor industry. I would like to the viewers to subscribe to the channel. We're uploading weekly podcasts on YouTube, LinkedIn. Please subscribe here. Here's the link. And we'll see you next week with another great power player of the industry.